We have misunderstood the universe. Those are not words chosen for dramatic effect. They belong to Adam Rees. The Nobel-winning physicist and Johns Hopkins professor helped discover the universe's accelerating expansion, spending his career refining some of cosmology's most precise measurements. He said them after looking at his own data, and he meant them. For the past decades, scientists believed they had the universe figured out. A single, elegant framework explained everything. How it began, how it grew, and where it was heading. Dark matter held galaxies together. Dark energy explained why space kept expanding faster and faster. The model worked beautifully, until it didn't. For decades, the model explained almost everything scientists pointed it at. Or at least that is what everyone believed. But buried inside the model was a number, a single measurement. And that number was about to become a problem nobody could make disappear. The trouble starts with something called the Hubble constant. It measures one thing: how fast the universe is expanding right now. Not historically, not theoretically. Today. You would expect two independent methods of measuring the same number to agree. That is how science is supposed to work. They didn't. The first method reaches backward in time. The European Space Agency's Planck satellite spent years mapping the cosmic microwave background. The faint radiation left over from when the universe was roughly 380,000 years old. From that ancient signal, physicists extracted the conditions of the early universe, ran the Standard Model's equations forward nearly 14 billion years, and calculated what the expansion rate should be today. Their answer: approximately 67 kilometers per second per megaparsec. A prediction built from a universe 14 billion years in the past. The problem was what happened when scientists measured the universe today. The second method measures the present directly. Rees and his team built what scientists call a cosmic distance ladder. A chain of measurements beginning with nearby pulsating stars called Cepheids, stepping outward to distant galaxies, and ultimately calculating the expansion rate from how fast those galaxies are receding. His team's answer: approximately 73. A gap of 6 units. In a field where precision routinely reaches 1%. That 9% discrepancy is not a rounding error. The early universe method said 67. The direct measurement said 73. Think of it this way. If you and a friend both measure the same room and get answers 6 feet apart, one of you made a mistake. But in cosmology, that 6-unit gap represents a universe whose expansion rate is significantly faster than our best model predicts. It is the difference between two pictures of the same universe that refuse to match. At least one piece of the picture had to be missing. But neither team could find the mistake. That's when they pointed the most powerful telescope ever built directly at the problem. For years, the leading explanation was technical. The Hubble Space Telescope, when observing Cepheid stars used to calibrate the distance ladder, sometimes blended the light of nearby stars together. That blending could make those stars appear brighter and therefore closer than they actually were. Correct for that blending, many argued, and the two numbers should converge. The problem seemed solvable. It wasn't. When the James Webb Space Telescope turned its instruments toward the same stars, it saw them with a clarity Hubble never had. Webb's infrared sensitivity cuts through dust and crowding in a way that fundamentally changes what is visible. If blending was the source of the error, Webb would expose it. The Cepheids would look dimmer. The distances would lengthen. The expansion rate would drop back toward 67. Many researchers expected exactly that. Before the data came in, the prevailing mood across the field was cautious optimism, that Webb's sharper vision would quietly deflate the tension and restore confidence in the standard model. Some astronomers were already treating the crisis as essentially solved. Webb, they believed, would simply confirm what the model had always said. The numbers were expected to converge. That is not what happened. In early 2024, Rees's team published a paper in the astrophysical journal Letters confirming they had used Webb to examine the full range of Hubble's Cepheid measurements. 1,000 stars across 5 galaxies, the most distant of them about 130 million light-years away. Webb confirmed Hubble's numbers, not approximately, almost exactly. Rees was precise about what that meant. With measurement error ruled out at high confidence, what remains is the possibility that our understanding of the universe is incomplete. At an earlier conference at the Kavli Institute for Theoretical Physics in California, Nobel laureate David Gross had told him to stop calling it a tension and stop calling it a problem. They should call it a crisis. And then, before cosmologists had finished processing that, the telescope found something even stranger. Webb was not only designed to measure expansion rates, it was built to look deeper into the universe's past than any instrument before it. And looking deep into space means looking back in time. The light arriving from a distant galaxy left it billions of years ago. The further Webb looked, the younger the universe it was observing. What it found there did not match what the standard model predicted. Early galaxies, those existing only a few 100 million years after the Big Bang, were expected to be small, chaotic, and still assembling. Raw material in the process of becoming structured. The logic was simple. Structure takes time, and time was scarce in a young universe. They weren't small. They weren't chaotic. Mike Boylan-Colchin showed that some early galaxies discovered by the James Webb Space Telescope were so massive they pushed the limits of the standard cosmological model. Explaining them would require nearly all available gas in their dark matter halos to become stars, far above the roughly 10% efficiency normally expected. Efficiency here means one thing: how much of a galaxy's gas actually becomes stars. The usual answer is about 10%. These galaxies would need almost 100. There's a reason that almost never happens. In standard galaxy formation models, star formation regulates itself. Radiation, stellar winds, and supernova explosions push gas back out before it can all collapse into stars. Picture a cloud of gas vast enough to build a galaxy. In the normal universe, only a thin slice of it ignites into stars. The rest drifts off like smoke from a fire that never fully catches. These early galaxies are the opposite. Almost the entire cloud burning at once. Physics does not work that way, not in the models scientists were using. The initial reaction among researchers was alarm. But then, just as the crisis seemed to be deepening, something unexpected arrived. A correction. In 2024, University of Texas graduate student Catherine Chworowski reanalyzed the Webb data and found the source of the confusion. Many of the supposedly massive early galaxies had been misidentified. Tiny, compact objects, nicknamed little red dots, hosted supermassive black holes consuming gas at an extreme rate. That process radiated enormous amounts of light, blending with the galaxy's own starlight and making ordinary galaxies appear far larger and more massive than they actually were. A trick of the light. Remove those contaminated objects, and suddenly the remaining galaxies fell back into line. The masses made sense. The Standard Model held. For a moment, the scientific community exhaled. Researchers who had spent months puzzling over impossibly massive early galaxies finally had an explanation that made sense. Conference presentations shifted in tone. Papers began framing the crisis as a misreading rather than a genuine contradiction. The alarm had been a false alarm. The crisis, it seemed, had been diffused. But it hadn't. The problem was smaller. It had not disappeared. Even after removing every misidentified object, roughly twice as many massive early galaxies remained as the Standard Model predicts. Not enough to break the model, but enough to leave a question nobody could cleanly answer. And it wasn't just the numbers. In early 2025, Webb found a large, well-formed spiral galaxy existing within the universe's first 2 billion years. A structure that usually requires calm, orderly growth to develop, in an era when the universe should have been too chaotic to allow it. Too organized, too many, too soon. The model handles most of what Webb is finding. It does not handle all of it. And the deeper Webb looks, the wider that gap becomes. Nobody knows whether these mysteries are connected. The Hubble Tension and the early galaxy problem could point to the same missing piece of physics, or they could be entirely separate problems. Two cracks in the same model. Scientists are exploring several explanations. Early dark energy models suggest a brief burst of expansion soon after the Big Bang. Modified gravity theories propose gravity behaves differently on cosmic scales. Direct collapse models argue enormous primordial gas clouds formed massive black holes directly, helping structures grow much faster than expected. None of these has been confirmed. None cleanly solves every problem. That is where cosmology stands today. Right now, an entire generation of instruments is being built to hunt for the answer. NASA's Nancy Grace Roman Space Telescope will measure dark energy with unprecedented precision. The European Space Agency's Euclid mission is already mapping the universe across billions of light years. Future Gaia data releases will refine Cepheid distances and remove one of the last major uncertainties in the cosmic distance ladder. The search is accelerating. The answer remains elusive. The data keeps coming. The Standard Model is not broken. It still explains the cosmic microwave background with extraordinary precision. It predicted the abundances of hydrogen and helium forged in the universe's first minutes. It accounts for the clustering of galaxies across the largest scales we can observe. No competing framework comes close to matching its track record. But it is developing fractures that were not there a decade ago. Rees put the current situation plainly in December 2024. Two NASA flagship telescopes now confirm each other's findings. We have to take this problem seriously. The most precisely measured universe in history is giving us two different answers at the same time. Both appear to be correct. And here is what makes this moment different from a routine scientific disagreement. Cosmologists have seen this pattern before. In the 1990s, cosmology faced a crisis that appeared impossible to resolve. Observations seemed to contradict the Standard Model, and no one could see a way through. Then the contradiction led to a discovery: the accelerating universe, and with it, dark energy. What looked like a fatal flaw became a doorway into something larger and stranger than anyone had imagined. First, the discrepancy, then the crisis, then the discovery. The question is whether history is about to repeat itself. Somewhere inside the space between the two answers, in the physics we haven't yet identified, the ingredient we haven't named, the property of space and time we haven't thought to look for. Something is waiting to be found. Cosmology has been to this edge before. What it found last time changed everything we thought we knew. Whatever is waiting on the other side of this one may do the same.